Now we will go through another type of isomerism, which is tautomerism. So basically tautomerism is a special type of functional isomerism, right, where you will see different functional groups in different isomers, right, where a compound that have same molecular formula, the two isomeric forms of this compound, right, will exist in dynamic equilibrium with one another, right. For example, you have two isomers, say isomer 1 and you have isomer 2, right, of any compound, right, say any compound. Now these isomers will have same molecular formula because they are isomers. We know that isomers have same molecular formula, right, but they have different structural formula. So there is difference in the structure of these two isomers, right. We will be looking into what is the difference in the structure of these two isomers. Now the important thing in tautomerism is that these two isomers are in dynamic equilibrium with one another, right. When we say dynamic equilibrium, that means I put equilibrium sign, this isomer converts into this isomer, right, anytime, and this isomer can convert into this isomer. So these two isomers can interconvert into one another, right, through the movement of one atom, right, which is generally hydrogen atom, right. So both forms can interconvert into one another through movement of an atom, right, generally hydrogen, right, and these two forms are called as tautomers, right. We call these forms as tautomers. So the isomers, right, in case of tautomerism, the two isomers are called as tautomers, right, and we also call tautomerism as desmotropism. Right, we call it as Desmotropism, right. This is a Greek word. Desmotropism is a Greek word which means, desmos means bond, right, tropism means turn, right. Desmos means bond and tropos means turn, right. So Desmos Tropism, right, which is another name for tautomerism, this word is made from two words, desmos and tropos. These two are Greek words. Desmos means bond, tropos means turn, right. That means you turn or move, right. That means your bond is this word desmotropism is given to it, or from this word desmotropism it indicates that a bond is turning or moving between the two isomers, right. We'll see how. So here the bond moves between two isomers, right, and like I said, it's a special type of functional isomerism, right. Now let's just recall. We said that tautomerism is a special type of functional isomerism. When we say functional isomerism, we mean that these two isomers have different functional groups, right. Now these two forms, right, can readily interconvert into one another, right, and this interconversion can be catalyzed by an acid or a base, right, and they can readily convert into one another on their own, right. So we also call this as, now the two forms interconvert due to a moving atom, right? An atom moves within the molecule, right? This is a change is happening within the molecule, right? So when a change happens within the molecule, we call it an intramolecular change, right? So due to this intramolecular change, atom will move within the molecule, right? So when an atom moves within the molecule, this bond also moves, or a bond will interconvert. Like a single bond will change into a double bond, or a double bond will interchange into a single bond, right? We'll take an example, then we understand. We call it a Desmos Tropism because here a bond is moving, right? In these two isomers you will see a bond is moving, right? So we also call it as Desmos Tropism. So important, it's a functional isomerism. A bond is moving between the two isomers, and these two isomers can readily interconvert, and this interconversion can be catalyzed by an acid or a base, right? Now let's take an example. We have this type of, the tautomerism exists in hydrocyanic acid, right? Hydrocyanic acid will exist in two isomers, this hydrocyanic acid and this is your isohydrocyanic acid, right? So if you apply all this, what we have studied here is, you have this is a functional, like I said, the first point, tautomerism is a special type of functional isomerism, right? That means the two forms have different functional groups. So here we have a CN group, here we have an NC group, isocyanide group, right? So these two forms have different functional group, right? And the interconversion and this cyanide form, cyano form, can readily convert into this isocyanide form, and this isocyanide can readily interconvert into this form, cyanide form. And this interconversion can be catalyzed or assisted by an acid or a base, right? So now you can see here a bond is moving, right? Here you have this indicates a coordinate bond, right? And here you have a single bond, right? So one bond is changing into a coordinate bond. Now when this form converts into this form, your coordinate bond turns into a single bond, right? Or a pi bond. Now if we look at another example, this one, this is nitroethane, right? And this is isonitroethane, right? So these two are also tautomers, right? The two forms which are in dynamic equilibrium are your tautomers, right? So let's look at nitroethane and isonitroethane. This is your nitroethane, this is your isonitroethane. Now one thing I forget to tell you here, you can see that the atom which is moving is your hydrogen atom, right? Here hydrogen atom is connected to carbon, here hydrogen atom is connected to nitrogen. So here your hydrogen atom is moving. Now applying the same concepts that we learned here to the second example, it's a special type of functional isomerism, right? So here you have a functional group double bond O, here you have OH, right? And you have this is Desmotropism, so a bond is moving, right? In this form you have a double bond, in this form here you have a single bond, right? So a bond is moving, right? So if you look at this, here you have a double bond here, here you have a double bond here, right? At this position. So position of double bond and hydrogen atom is changing together. When this hydrogen atom is moving from this carbon atom to this, right? Your single bond is also moving between nitrogen and oxygen here, right? And your double bond is has moved between carbon and nitrogen, right? Here it has moved between carbon and hydrogen. So here these two are isomeric forms which are in dynamic equilibrium with one another, right? Nitromethane and isonitromethane, and they can readily interconvert, right? Nitromethane can interconvert into isonitromethane, and isonitromethane can interconvert into nitromethane. And this interconversion can be assisted by an acid or a base, right? and you have a bond moving between carbon and nitrogen, right? Single bond is moving into double and double is moving into single, right? And this is due to a mobile atom, which is hydrogen, right? Here hydrogen is moving between oxygen and this carbon, right? You can see that here this one hydrogen atom from this CH2 has moved to this oxygen atom, right? And here this is your keto form. This is, I'll just come to this, but before this there are different types of tautomerism, right? And there is one important tautomerism that we will be studying here. This is your KetoEnol tautomerism, right? This is your keto and enol tautomerism, right? In KetoEnol tautomerism, the two isomers, right? One isomer, since I said this is a special type of functional isomerism. So in one isomer has a functional group of ketone, right? And the other isomer has a functional group of alcohol, enol. Enol is for alcohol. So here you have a keto form which is in dynamic equilibrium with enol form, right? Keto form represents your OH and enol form represents your OH, right? Now this functional group changes into this and this changes into this. It's due to a mobile hydrogen, right? When this mobile hydrogen moves, a bond also moves, right? Now this bond movement and hydrogen movement, we call it as intramolecular change, since it is happening within the molecule. This is an intramolecular change, right? Intra means within, molecular is molecule. So within the molecule, this change is happening. Change is movement of hydrogen and your bond, right? So this is an important form of tautomerism, which is your KetoEnol tautomerism, in which isomeric forms, which is keto form and enol form, are in dynamic equilibrium with one another, and this equilibrium or the change of keto form into enol form and enol into keto form can be assisted or catalyzed by an acid or a base, right? And we'll see how the bond turns here, right? Here this is the example of KetoEnol tautomerism. You can see this is your acetone, right, where you have a ketone group, right? You have a carbonyl group, basically we call it a carbonyl group, and this is your OH group. So here you have a carbonyl group. In this enolic form you have a OH group, right? Now these two forms can interconvert readily into one another, and they interconvert into one another due to movement of a hydrogen atom, right? You can see this hydrogen atom is moved from here to this oxygen atom and has changed into enolic form, right? And at the same time, since we say it's a Desmotropism, so your bond is also moving. Your bond here, double bond, has moved in this form between these two carbon atoms, right? And when this form changes into this double bond will move between carbon and oxygen in this form, right? So here this change is taking place within the molecule. So it's an intramolecular change, right, which is due to mobile hydrogen, right? And a bond is also moving at the same time. This is your KetoEnol tautomerism, right? And the two isomeric forms, or the two tautomers here, are keto form and your enol form, right? Now when a keto form changes into enol form, right, when we say a keto form changes into an enol form, right, we call it as enolization. This is your enolization, right? Change of keto form into enol form. And how will this change take place? By the movement of a hydrogen atom, which is a labile, we call it a labile hydrogen atom, right? which is a labile hydrogen atom, due to which the keto form will change into enol form, and this change, right, where enol form is formed is your enolization, right. Now the two forms, the keto and enol forms, there is one important thing about keto and enol form is that these two keto and enol forms doesn't have the same stability. One is more stable than the other, right. Here this form, generally keto form is more stable than the enol form, right. Keto form is generally more stable than the enol form, right, and the less stable form we call it as the labile form. Less stable form is your, we call to the less stable form as the enol, as the labile form, sorry, right. So mostly your in KetoEnol tautomerism, your keto form is stable than the enol form, right, but in some cases the keto form is less stable than the enol form. For example, if you take the example of phenol, right, this compound, here you can see you have CH here, right, here you have a CH. When this H will move here, it will change into phenol, right. So when this change, right, and when this hydrogen atom will move back to this carbon, right, you have a bond moving, right, this double bond will move here. Now when this hydrogen will move to this carbon atom, right, now again you see a double bond. This double bond will move between carbon and oxygen here, right. So bond is moving, right, hydrogen is moving, so a bond is moving, right, in this keto and enol form. But there is one important thing, like I said here, mostly the keto form is stable than the enol form, but here your enol form, this is the enol form where you have an OH group, and this is your keto form, right. Here enol form is more stable, right. Why? Because due to an intramolecular change where your hydrogen moves to the oxygen atom, right, where your hydrogen moves to the oxygen atom, what is getting formed due to this change is a benzene ring, right, which is an aromatic ring, right. Now since you have an aromatic ring here, we know that aromatic ring is stable ring, this benzene ring is stable ring. So due to the formation of benzene ring, this enol form is stable than the keto form, right. So this is an exception, or in this case your enol form is stable than the keto form because of the formation of benzene ring, that gives stability to the enol form, right. Now there is one more important thing, that the change, right, the change of one form into another form will take place, or the change of keto form into enol form will take place only if you have alpha hydrogens. Without alpha hydrogens, this change will not take place, or compounds that do not have alpha hydrogens will not show KetoEnol tautomerism, right. But in this case also you can see that if these are alpha hydrogens only, right, where hydrogen is moving, right, and due to this movement you have these two forms, nitromethane, nitroethane and isonitroethane, right. So if we talk about this acetone, in acetone you have alpha hydrogen. Alpha hydrogen is firstly the carbon which is next to the carbonyl carbon is your alpha carbon. This is your alpha carbon and this is your alpha carbon, right, and hydrogen atoms attached to alpha carbon are your alpha hydrogens, right. So you have alpha hydrogens here which can move, right, between oxygen and this carbon atom, right. So if you have, for example, C6H5, right, CHO, right, this will not exhibit tautomerism, right. So you need to have an alpha hydrogen, right. If you do not have alpha hydrogen, KetoEnol tautomerism does not exist, right? For example, it is not possible in, like I said, C6H5CHO, right, but is possible in CH3CH2CHO, right, CH3CH2CHO. In this is your, these are your alpha hydrogens. So here KetoEnol tautomerism is possible in this compound because you have alpha hydrogens at this carbon, right? So alpha hydrogens should be there in the compound in order for a compound, right, to show KetoEnol tautomerism, right? Because it is this alpha hydrogen only that moves, right, and due to which it converts into the other form, right, like the enol form, or the enol form converts into the other form, right? So this is important. So I'll just mention it over here. Alpha hydrogen atoms are required for a compound to show KetoEnol tautomerism. Right? So I hope all this is clear. Thanks.